It's Monday, right? We had a weekend. It went so fast, I lost it, but we're back. And up on the calendar, we see this week we have just two sections. So we'll do 9.3 and then 9.4. Um, this is sort of an entryway into statistics. And I must say this lesson today, I really liked it. I've done this. It was a little different than anything of how I approached this topic before, and it made a lot more sense. And even though I did my graduate work on it, you'll see. I think I understand it actually better now. So after going through it, and I hope the same thing will happen. I haven't looked at 9.4. I know sort of generally what it's going to do, but I'm interested in seeing its approach. It can make it hopefully very understandable. Friday we'll have sort of an open work day, I'm sure, because today's lesson's not too long. I'm assuming the same thing for Wednesday. So we have space during this time. We'll pick up 9.5, which is a little bit bigger. It may go over 2 days. We've got our last topic there on that Friday and a whole week for review. So this series, and again, we're not going back on the test. We'll not go backwards. As you see, some of the concepts we've learned, we're using them again, but we're not going to directly test you on stuff from like test 2. It'll be incorporated in what we're doing. So first, let me just do a real quick assessment, real quick test. What is 2 plus 2? 4. Okay, good. What is 4 divided by 2? 2. You're all set. You know everything you need to know to understand today's lesson. We're basically just adding a bunch of numbers and dividing by however many numbers we have. That's the hardest part of today's lesson, maybe. So from that perspective, but we do get into, the application of it is actually fairly powerful on a business sense. So we're going to be talking about measures of central tendency. Sounds like a big idea. It's basically, where's the middle? Where's the middle? That's all this question we're asking. Where is the middle? So we've got data. What's the average? What's in the middle? And there's going to be 3 different ways we look at it, because depending upon what the data is, one might be more valuable to us than the other. But where is the middle of the data? What's the average? That's really all that today's question is about. So, and I left a lot of the wordiness into this. So we're going to measure popularity, rating of your statistics instructor. And so ideally we would want to, if we want to find something out, we should, like Mr. Pellegrand, we should ask all his students, what do they think about him? Everybody to rate him. That would be what's called a population. So if we ask all the people, so some of this is sort of just introducing vocabulary. However, Mr. Pellegrand teaches 400 students a semester, which is not on, he must be here, because that's, I do 400 to 600 a semester. So that might not be doable. Not everybody's going to respond. So we probably won't get a population, but what we will get instead is we'll take a survey, and that will be a sampling of his students. And as you get into statistics theory and stuff, what you'll see is actually samples sometimes can be more accurate than trying to get a whole population. It's kind of, I call it anti-intuitive. It's not intuitive, because you think the more you have, the better picture you have. But if you go for a population, you really have to get everybody. And so missing a few on a population actually can throw things off more than anything. Large samples are great, but also we won't get into it in this class, but if you do take a statistics class, you'll see sometimes if you have a very large sample, that actually in itself causes problems. There's, you might have seen it in the news, Facebook was able to say certain things, but they just had such a huge number. The sample was actually too big, and they basically allowed them to say almost anything they wanted to say. So that's how the theory works. So actually, it's weird, but with statistics, sometimes, most of the times, a reasonable size sample is what we want. Smaller is oftentimes better than bigger. Not too small, but but it's that misconception we might have that the more data, the better, right? Not always, not always. So here we have survey results. And you can see them listed here, not in any particular order. They're rating them from 100. So this student here at 100 really liked Mr. Pellegrade. The student at 0 didn't like him very much. So, and that happens. So sometimes we get this sort of polarizing. Somebody, really likes him, though. So that's part of what we're going to get to on Wednesday is the spread of the data. Today, we're just looking where's the middle, but the middle isn't always the answer we're looking for, okay? Because we have these two extreme ends, right? So how could we answer this? Well, one thing we could do is kind of get at to what the average is. We're looking for what's called a statistic. So we're trying to, instead of looking at all the data, we want to get a single number that sort of represents that data, right? So when we talk about a statistic, it's been a calculation to take all the data and make it into like a single number. And so one of the single numbers we can use is called the mean. And generally we call that the average. Now the average can be applied to these other two that we're going to talk about, the median and the mode as well. But when people said, I want to know the average, usually they're talking about the mean. But be careful, they might be talking about one of the others. But that's typically what we figure. And the way to get a mean is we add all the data together and divide by the number of pieces of data. So there were 10 pieces of data. Again, just like I said, 2 plus 2 is 4. 4 divided by 2, you just took an average of two numbers, right? So that's what we did at the beginning. And here we add all 10 together. We got that all adds up to 525, divide by the 10. So we could say the average rating for Mr. Pellegrand was 52.5. And that's exactly what we do here. So I don't know if it's available now, but you'll get a survey that you get to rate me and the course. And they average all of those, and I get a rating of whatever it is. And then they compare me to the average of others. And but again, is that 52.5? Does that sound like you have a 52.5 popularity rating out of 100? Half and half. But again, is it really representative? Well, here's 100, here's a 90. So some students just really like him, some don't. But anyway, this is how statistics work. So the other thing is, as we get into this, I want to hopefully get you to be skeptical about statistical numbers. Just because that's the median, mean, what does that really mean? Sometimes we do want to look at the whole picture, okay, to see what's happening. And then we don't even get into this class how the sampling was done, right? Because you might gone to this corner of the class, and those are all the students who don't like them very much, and that's why they sit wherever they sit, and then maybe, or you might have measured in this part of the class where everybody likes them, and that's why, who knows? So there's all that sort of stuff. But today we're just saying add them together, divide by the number there is, that's the mean, that's the average. We're going to also look at some mathematical formulas or short ways of writing it shorter. So when we use a sample, we use this symbol for the mean, X bar. And you'll see this if you have a TI calculator, it will calculate the average for you, and it has a little X bar. That's a sample mean, okay? And then this listing of X1, X2, X3, those are just the data points. So those are the scores everyone gave them. And the last one, there would be 10 there. And then N is the number of people that were surveyed, which in that last case was 10. Okay, so we're just using some letters to stand for numbers in general. Okay, and we're going to make it even more abstract so that we can, compact it. But the thing is you'll be able to look at these symbols, and instead of just saying, wow, that looks weird, or maybe it must be really advanced, it's not. It's just a shortcut for writing, add them together and divide by however many there are. So we can write the sum as this symbol. I mean, I remember when I first saw that, oh, what's this? It's a big sigma, which is a Greek letter. And so that a lot of times in math, they do that. They use Greek letters or some other, so it's really a foreign language in this case. The sigma, because S for sum or adding. So it's just kind of like a little, machine. It's telling us to start at the first one. So x sub 1 is the first piece of data, and keep adding them together until you get to the last piece of data. That's all this is saying. And so by itself, if there was no x sub I, you can use this symbol just to say add the numbers 1 to n. So if n is 100, this just would mean add from 1 to 100. Okay, which is kind of an interesting way to do it. But then if we put a formula inside it, this is telling specifically whatever x is. Okay, so the first x, second x, third x, and it simply means do this. Add all the data together. But that little sigma, again, I remember when I first saw this, it was so foreign to me, it threw me off, right? Because this must be something really, but it's just a shortcut. It's not too, it's just a shortcut way of saying add everything together. Okay, we okay with that so far? And again, we won't have you necessarily using it, but you might see that in a problem. So, okay, so add the numbers together. The sum of 1 to n. So all we're doing is taking the data points and adding these together. So just again, some language. A sample is the values or scores. What we do is we assign them and we think of them as a random variable. Again, we're still probably struggling what really is a random variable. It's just a technique of giving a number to an event that happens, right? So, it's when it's a dice and then there's the numbers 1 through 6, those are actually just dots on it. There's 6 dots on it. We say the random variable of a dice with 6 dots on it is the number 6. So random variable is just a way of assigning it a number. So some of these, we could do a sample. We could sample something and we could sample colors, red, blue, green, and then we could assign numbers to those colors. And then we could do the statistics, because statistics, primarily what we need numbers. And so this is a way of taking something, or we take people's opinions, right? That's really what we're doing, is we've asked them what's your opinion of, and give it a number. Or how much pain are you in, from a 1 to a 10, right? That's a hard question sometimes. I don't know. It hurts a lot. Is that a 10 or is it a 5? Or I don't know. But anyway, so it's somewhat subjective, but we get a number. We're able to do some math with it. We're able to get an average. Okay. And then we're able to take a sample mean. Okay. So that's primarily what we're working with. Thinking of populations is lots of people usually, and we're just going to do the few. And so we just go to this, we just took our formula, the mean, the x bar, because it has a bar on top, we could just call it x bar, add all the x's together, all the data, divide by however many there are. We can now shortcut it with this formula, which just says add all the x's together and divide by however many there are, in, right, in numbers. Okay, so that's, a lot of this is, we're just going to do this, but I wanted you to see it because you may see it in the homework, and I don't want you to be thrown off by it. It's just a way of, it's a little machine. Okay, put in the 1, then add the 2, x2, x3, x4, x5, all the way up to, in that last case, x10, and then divide by 10. Okay, so you'll see this listed somewhere sometimes. N is the sample size. It's how many pieces of data we have. And then we're just adding all the data together. So then what really does the mean mean? What is the average? It means it's a balance between the average. So these pieces of data down here, 8, 5, and 2, if you add them together and divide by 3, you get 5. And so what it's saying is, if we were to think of the data as a single thing, they would all be 5s. That would be a balance. Okay, everyone's at a 5. It's not accurate, right? Someone's getting, especially if this is salary, there's one person getting 5, but someone's getting 2 and someone's getting 8. So again, it gives us just an overall picture, maybe how to compare 2 different samples, right? But within the sample itself, we're still going to need that extra information we're going to talk about on Wednesday, the spread, how spread out is the data. Because the data where we had 5, 6, and 4s, is different than ones that are more spread out. So we'll talk all about that. But today, we just want to know where the middle is. And that's kind of a picture of what the middle means is once we've got the average, we could think of it as every piece of data could be that amount. That's an average. If we get the population mean, which again, there's problems with that, but occasionally that can be done, or we get so much we call it the population. We just use a new Greek letter and we call it mu for the mean of the population. And again, we're not going to get too I mean, if we were in a statistics class and doing this all semester, you would see a lot of these. So that's part of what I want to get you prepared for is I know a number of you will go into statistics because you're going to need to. So when you see these, I want you to say, oh, it's not so scary. It's just, I've never seen that little thing before, but it's just a mu. It's just saying this is the population. X bar is the same thing. It's a mean, but it's the mean of a sample. So, and that's the basic thing we have in statistics. We have those two things. We have either the population, which is everything, everybody, and we have a sample, which means we just sort of drew blood out, a little bit, and we're going to see what that sample tells us about the population. Okay, so here's some examples. The mean of the sample, 1, 2, 3, 4, 5. Add them all together, divide by 1, 2, 3, 4, 5, and you get 3. I think if you add them together, you'll get 15. 15 divided by 3, right? Oh, wait. 15 divided by 5. 15 divided by, because there's 5 pieces of data. That's where we got the 3. See, is that really 15? Yeah, because 4 is, that's 5, 5. There's 3 5s. Okay. This sample mean, they actually show it to us, so we add the numbers, and if they're negative numbers, that we just add a -1. So we end up with -1 plus 2 is just +1. There's 3 numbers, so our average is actually 1/3. Okay. Not even one of the numbers. And then this last one, -3, -3, 0, 0, 1. Again, add them all together. There's 5 numbers, so divide by 5. And if you do that, we actually end up with a mean being -1. So that would be about the middle of that data. So far, so good. Add, divide. That's all there is to it. So we're trying to get to the center of the data, the middle of the data. We call that central tendency. That's another phrase that just threw me off for years. I said, okay, I figure out. It just doesn't, it's even now, it doesn't, it's kind of so abstract. I know what the middle is. That's all it is. Central tendency, the tendency to be towards the middle. So there's 2 other measurements, though, that we could use. And the reason is because data looks differently. So there's the median, and those are the 2 main ones we will use, either the median or the mean. We'll talk about the median. And the mode also can sometimes come in here. So sample median is the same thing. It's a median that's arrived at using just the sample, but it's a located score. It's the middle one. So what we have to do first is we have to get the data in order, and they say ascending, but it could be descending. It doesn't matter, but they have to be either from smallest to largest or largest to smallest. It doesn't matter, but they have to be in order, numerical order. And then we physically locate where the middle would be. And that's what this is saying. If it's odd sized, so that means like if there were 11 being odd, there would be 5 on one side, 5 on the, and there would be 1 in the middle. So when we have an odd sample, and not odd as in strange, but odd as in odd number, 11, 13, 9, we will actually have a physical piece of data in the middle, and that's it. That's our median. So it's a location, not a calculation. Think of it. The mean is a calculation. The median is a location. We just have to get it in order. Oop, there it is. However, if we had an even number like 10, we've got 5 and 5, there's a space in the middle. So what we do is we average the 2 middle ones. So the 5th and the 6th, we add them together and divide by 2. So it's kind of finding halfway between the space. Okay, and that's what it's saying here. In the case of an even size sample, we find the average of the 2 middle pieces. Does that make sense? Okay, and again, there's calculators that will do all this thing. TI-84, you can just enter it in. And when I'll do some samples, I'll show you how you can do that. You enter it in, you hit a certain button, that's the stats button, do one variable statistics. It'll give you the mean, the median, the mode. It'll give you everything. It'll give you the standard deviation as well. So when we get to Wednesday, but in one screen, you just go through and it'll give you all that data. All those, sorry, not the data, all the statistics from the data. Okay. A sample mode is just the one that appears the most. And again, this is, I don't like calling this a central tendency because it could be the low data occurs the most or the high data occurs the most. It may not have anything to do with the center, but it's a different way of viewing what the center would be. The center is whatever happens the most, right? This is what's happening and it's at this number, not, so, but it might not be anywhere near the mean or the median. And they've got an example in here that will show that. But occasionally it's another measurement that gives us a picture of what's happening. Okay, and again, in a company, this might be a thing we do. The CEO who makes $20 million a year may say, "Well, our average salary is $500,000," and you get this idea: everybody's making $500,000. Well, it's because the CEO is making 20 million and everybody else is making $15 an hour or something. The workers may want you to look at the mode because out of 200 people, maybe 190 of them are making this lower wage. That's the mode. For them, that really is the middle. That's what they're talking about. We need to take some money from the top and let's spread it out. Okay. So this is a thing where you get a discussion of where is the middle, and depending on perspective, you could both be telling the truth you're using different ways of a different lens. Okay, so again, we'll just I could get talking about all this stuff for a long time. So here, the mean and the mode, again, for the median, the mean and the mode. So the median is the middle score. So if we have to have them in order, and since there's 1, 2, 3, 4, 5, 6, 7, that's an odd number. Notice there's 3 above and 3 below. And so the median is this middle piece here. The mode is the one that happens the most. And so there's 3 occurrences of the number 2. That's a mode. 4 and 8 only occur twice. And actually, they don't give us the mean. Let's do that real quick. To get the mean, it would be 2 plus 2 plus 2 plus 4 plus 4 plus 8 plus 8, and then we're going to have to divide by 7. Let's see if that's 10, 10, that's 20, 30. Not bad. I think that adds to 30. Divide that by 7. It doesn't go evenly, but that would be 4.4 and 2/7. 4 is 28. 2/7 is point something. I don't know. I'll say approximately maybe 0.2. Somebody figure, anyway, something, right? 4 point something, which is about where the median is, right? That would be like right here, a little bit bigger than that one. It's not actually a piece, so we'll put that in there. And so we see these 3 measurements: mean, median, and the mode. They're different measurements of where the center is. Primarily, we'd say, okay, it's got about, if we're looking for an average, about 4 is pretty good. Okay, and as before, if this was all the data in the population, and that it could be these are the weights we have. We want to find what our average rate is, or the central. This could be a population, but it also could be just a portion. It could be a sample. So we need to know, and again, if this is a sample, for the mean, we'll use X bar. If it's a population, we'll use the Greek letter mu. And typically, with the median, I don't know that there's a special, I haven't seen a special one for the median. Okay. So the sample of this data giving us, again, the thing is we don't want to just say, oh, look at all this data. There's 1, 2, 3, 4, 5. There's the middle piece. We're done. Is that right? No, because I got to get it in order first. It wouldn't make, because I could randomly put it in any order and take that middle piece and I could get various different values, right? So no, that's not the median. I got to get it in order first. The median is the middle number when it's put in order. Okay, so that's, and again, it's a mistake I see too often. And sometimes it comes from multiple choice tests that just give you the data and you say, oh, there it is, it's in the middle. But you have to get it in order first, okay? So sample mode is 2, because that's, again, it's locating it. There is no calculating in this case, just locating. Again, if it was an even number, if we had 6 pieces of data, we would have had 2 in the middle, and we would have just added them together, divide by 2 gives us the middle piece. So in this case, 1, 2, 3, 4, 5, 6. This is what they're going to do. And it's not in order, but if we got it in order, right, I guess we could do that -1, 0, 2, 5, 6, and 6. Here's our 2 middle numbers, 2 and 5. They add them together, divide by 2, so then we say our median is 3.5. Okay, so that sort of locating with a calculation. 3.5 is not actually a data piece, but it's what we know is it's about halfway between the 2 middle pieces. So it's a little more accurate way of doing that. Okay. And then 6 occurs the most, it occurs twice, so the mode would be 6. And again, here's a case where the mode is not really meaningful necessarily. It's certainly not in the center, it's at the far end, but it is a way of, it's what happened the most. Okay. But when you think of statistics, this is one, like I've taught it in all levels, MMM, which one is which, and I remember learning it. What's the mean, what's the median, the mode, they all got M's. Why couldn't they have given them some better names? I don't know. Okay. And this is a little statement about why we would use one over the other. The mean tends to be affected more by extreme values, like the CEO making $20 million makes the average salary seem like it's pretty high. It could also work the other way. We could have an extreme low values that could skew the mean over to the low end. So the same thing can happen when you have a piece of data that's way out, because it's getting added in. You add 20 million into everybody else's salaries, which might only be like 2 million. That piece itself has just really skewed out the data, where it won't affect the median. So you'll see labor unions will usually use the median salary, because that's for them it's more accurate. It's what the average worker is making. It kind of takes the extremes of the CEOs and those the board and everything who's making millions, takes them sort of out of the equation. I mean, they're still in there, but it's because we're just counting numbers, it doesn't affect it. When you do the average, that's what the board will usually use. Oh, we're paying an average of 500,000. Well, hey, I'd like some of that, right? No, you aren't. You're paying a lot of people up here, but what really is your average? So that's the use of it. You'll see in housing data, they will oftentimes use the median value. They don't use the mean, because you have the $20 million house that was put in among a bunch of other $200,000 houses. That would skew the mean way out there. And it would say, oh, everybody's average house value is high. No, it's not. It's one house that's a palace, and then everybody else is such and such, So we use the median to kind of in housing data. And so you'll see that, but just be aware as you consume statistical data, because sometimes they're trying to be, make you think in a certain way, and they're not really accurate. They could call both of those the average, but you got to ask what kind of average. That's why we use this specific language. It's the median, it's the location of the middle. If it's the mean, it's the sum divided by the total data, and the mean can get off there. And again, the mode is valuable if we have non-numerical data. We kind of like going with colors. What color shirt is everybody wearing? And so it makes sense. You can't really do math with that unless you make it into a very variable or something. But what we could do is say, looks like light colored shirts today is the most here. So that's the mode. So we could say that's sort of the central fashion survey. Okay, here's an example. We have a tin a 10-year survey of spending patterns of the U.S. teenagers in the 1990s, and we've got these dollars spent in a year. So 90, 90, 80, 100. So compute and interpret the mean, median, and mode, and illustrate the data on a graph. So we're going to do all of this. I'm just going to go walk through because it's just tedious. So the mean, all we do is we could use these symbols. We don't have to, but we're going to add all the data together and divide by the number there's 10. So that's what it looks like. Just add them together. That's 860 is what it comes to, divided by 10. So we could say 86 is the average spent over that 10-year time frame. Okay. Some more, some less, but that's the average. That's the mean. That's usually what we're talking. When we're talking the mean, talking the average usually. 86 billion per year. To get the median, we put them in order, not by year, but by value. So 80's at the end, 100's at the ends. And then since there's 10 of them, there won't be a middle piece, but there'll be two middle pieces, right? So 1, 2, 3, 4, 5 from this end. 1, 2, 3, 4, 5 from this end. So 85 plus 85 divided by 2, or you'll see whenever you have the same number in the middle, what's halfway between 85? 85, there is no middle. 85 is also the median. So that's how they got it. 85 plus 85 divided by 2. So that's our median. But again, just think, put it in order. And there's a few. I think there's maybe 3 or 4. We're going to, I got to keep moving. We're going to apply these to something called expected value in just a moment. And that's what most of the questions are about. So $85 billion. Okay, so pretty close to the mean, but not exactly. Okay, which one's a better measure? I don't know. And then the mode was 80 because that happened the most. But again, that's at the low end. And then we could do a histogram, and we see that, and it labels where the mean and the median and the mode is. And we can visually see the data. So a lot of times the visual representations are actually more helpful. We can see sort of where the center is, but we can also see trends and other things going on. We can see sort of missing data. Nobody spent 95, so it's this. But that's kind of what we do. We're not going to have. I think we've done some frequency tables or graphs, haven't we, in the homework where you had to drag it up? I thought I saw that. So we're not going to do it this time, but there it is. So now this is the majority. I can't remember how many homeworks. I looked over them, but there's maybe 3 or 4 that are just specifically, here's some data, give me the mean, median, mode. So that's what that is. Second part is going to be to get the expected value. Now, this first, don't get lost in this next few slides. I'm going to build up and show you that really the expected value is sort of is the mean from a probability perspective. Okay, and we're going to go through and we'll use the mean formula. We're seeing that some things cancel out. The final formula we use is more simple than what we start with, but we're just using this concept of we're going to add the data together, find its mean, and then use the probabilities as well. Okay, and that will give us sort of an expected value, which is really where's the middle of what could happen in a given situation. Okay. And we're using random variables, which again is some sort of abstraction, but just remember, random variables is assigning a number to that variable. So we'll look at a couple different. So we roll a fair die, and a large number of times, and that's the thing for expected value. It has this concept of it has to be a large number of times, because if we just do it once, anything could happen, right? But if we do it a large number of times, we should get close to that middle. That's the idea. Of course, maybe not an eclipse. Maybe the eclipse throws off gravity or something. I don't know. We could do that test today, right? No, we won't. So if we roll it in times, and again, you just want to think in, well, it's a big number, maybe 1,000,000 times, maybe whatever. Maybe we use a computer to do that. But we roll it in times the die, where n is very large. The probability of rolling each number, so rolling a 1 is 1/6. We would roll a 1 roll a 1 1/6 of the time. Or we did it n times, n divided by 6, right? So that's sort of looking the average number of ones we would get. And for each of them, we would, because rolling a 1, a 2, a 3, a 4, a 5, or 6, it each has a probability of 1/6. So we're going to see where we'll think of these in terms of probability. But this is getting us to think in terms of numbers, right? So that if we do it a large time, we should get about 1/6 of them should be ones, 1/6 should be twos, 1/6 should be threes. Does that make sort of sense what they're doing? And we're going to see that when we do the average, this is going to cancel out because we're going to divide by n, right? So those will go away and we'll get to something much simpler. But I like this because it helped me understand expected value in a sort of a newer way. So if we took the sum of all of those rolls, right, we would get a 1 1/6 or n/6 of the time. We'd get a 2 n/6 of the time. So this would give us the sum of all the rolls, sort of like adding all the rolls together. How many times did we get a 6? We got that n out of 6. So that, again, if we did it a million times, million divided by 6, whatever that is, times 6, that's how many 6s we have. So we could add them all together. That would give us a sum, right? This would equal the sum of the population, actually, because it's all the rolls we did. And then to get the average of those rolls, we would divide that by however many we did, which would be the n again, right? And so we'll see that this is what we get, which looks kind of complicated, but we can divide each of these by n, so those n's go away. And what we end up with is a very succinct formula where this 1/6 is now the probability of rolling a 1, and this 1 is the random variable assigned to rolling something with 1 dot. It's the value. And so as we multiply all of these, we get what's called an expected value, which is sort of an average value, which means if we roll it a large time and add them all together, that's about what we should get. And if you do that, you get 3.5. Does that make sense? 1, 2, 3, 4, 5, 6. That halfway. If everything's equally likely, we should be about. The sum should be about halfway if we did a large time. And we're going to, when we get to the normal curve, we see the bell-shaped curve. Yeah, that middle should be about 3.5. Now, can you roll a 3.5? No, you can't. But the mean oftentimes is a calculation that is not one of our values. If we did the median, we could do the same thing. If we could put it all together, we'd probably still get 3.5 with a large number of data. We'll see that. Okay. So far, are we good? So now we're going to start. Now you can take your notes because this gets into what the formula. This is usually where the talk of expected value starts. I never saw it as an average. And now that I see it as an average, it makes more sense. Because I always thought expected value, that's what you expect to happen. It's not. Because probability, you never get what you expect. It's the most likely thing to happen. Do it a large time, you'll get that. But it's not really that. So we call it the expected value, but just think of it, it's the average probability, right? It's the random variable with the average probability. So it is the expected value of the random variable for rolling a die. Okay, and n needs to be a lot, and yet we don't have to use it because it ends up getting divided out. Okay, so what we want to think of expected value is just whatever the probability is times each random variable. So this is how we're going to look at it. We've got this table of probabilities. We've got the x values, right? Here's the x values up here. Here's the probabilities, and we're just going to take each probability times each random variable. And so that looks like, well, what we did. So this is really all that's going on with expected value. We don't have to worry about n because it divides out. But having seen it this way, that it really is just an average, is much more meaningful to me, and hopefully to you too. Hopefully because I hold a lot of misconceptions about it, because I was thinking that's what should happen, because expected means it should happen, right? It's not. It's an average, and it could happen, and it's most likely to happen, but we still get some variation. Okay, so, but the calculation itself is usually not too bad if we've got a table. And in the homework, they will have you make up some of these tables, which we've done in previous lessons. But then now what we're going to do is we're going to say, what's the expected probability? If we did this a lot of times, we do it only once or twice, anything could happen, right? Especially here, we could get any number. But if we rolled it a million times, this would be the expected average. Okay, and they show that, yeah, so again, they get a little bit, more funky with the formulas. This is kind of expanding out, but it's just taking the sum of each random variable times each probability of that random variable happening. So we go to the table and we do that. So it becomes, that's what the other thing, it's really a prediction. I like that better than expected, because what do you expect is going to happen? It's almost too much faith in it happening, but it is a prediction, and it could happen, or we could be around that number, but that's what's going on. And again, the larger the sample, usually the more accurate we can be. So we'll relate it later. Okay. So here's an example. We've got this distribution. Again, we don't know how many times it's been done, but this is maybe some game or something, getting a -1. Maybe you're losing $1 on this game. That happens 30% of the time. You don't lose any money or don't win any money 50% of the time. Maybe you win $4 10% of the time. You win $5 10% of the time. So these are like maybe a game matrix. And if the expected value ends up being 0, that means it's a fair game. You don't expect to win or lose. It's fair for both sides, right? Most casino games are not that way. There's actually, the expected value is the casino's going to make some money, which means you're going to lose some money. Again, sometimes you come out a winner, but in the long run, the casino is the one that will always come out the winner, usually. Let me do this. So to calculate the expected value, we just take each x value, -1, times its probability, plus 0 times its probability, plus 4 times its probability, plus 5 times its probability. And again, I could do this, but they're going to calculate it for us, so I don't want to, we're getting close on time, so I just want to show they did it for us down below. We end up with a 60, the expected value is 0.6. So it means actually this is a good game to play. If we played it a lot, we would expect to win 60 cents. So that's in our favor. It's not a fair game, but it's one maybe in our favor. If it was a -0.6, then it would go to the other people's favor. And again, it just depends on how those probability distributions are laid out. Or this might be from the casino's perspective. So, and that's the other thing, is expected value, whether it's positive or negative, depends on what side of the table you're on. So for the casino, if this was their setup, they said, okay, we're going to make 60 cents per game on average. We'll let this one go, because yeah, we'll play this one. We're going to make money. From the consumer side, that means they're going to lose 60 cents each time, on average. Okay, so far so good. And that's all you need to know about expected value. We're going to tie in some other things. There's a few questions in there that get you to think of the average in a little different way, because I'll give you maybe the average, and so you'll have to do some calculations. I'll let you work through those. Again, those will be good things to come in on Friday if there's a few that might get you stuck a little bit. I want you to think about them, and we can talk about it. We'll get you through them on Friday. So this is what it's just talking about. If it's 0, it's a fair game. And so, yeah, if you flip a coin and it's heads and you get $1, or you get tails, the other person gets $1, that's a fair game. 50-50, each winning. But that's not what casinos do, right? Because they don't want to be fair. They want to make a profit. Although there is that might just be a 4%, but think about it: millions of dollars going in, 4% of millions of dollars. It's pretty good. So because they also want enough people to win that they're excited. If everybody lost, nobody would keep going back, right? I don't think so. So there's most games in gambling are biased. And just think about that. Even with sports betting, there's the way they set them up. There's a bias for the bookie to actually come out as a winner. Although it's a little different because maybe we really don't know what's going on unless, but there's a lot of games that are fixed that we don't know about. It's happened before. So most gamblers, again, the idea is that there's keep the losses to a small amount, but keep them consistent. So most gamblers will lose a little bit, but not enough to hurt them, hopefully, so that they keep coming back. A few will win, and then you think, oh, I want to be that one. That's why we buy the lottery, right? It's Powerball's up to 1.3 billion, unless it's been won. So people want to go in. I want to be the person who wins that. But the odds of winning, or the probability of winning, are no better today than they were 2 weeks ago. But the hype is, okay? So that's basically what we're doing. Casinos make a lot of money. Now there's a very simple probability that comes up when we've got a binomial. So this is tying back into what we just did on Friday, I think, binomial. And what's a binomial? There's two things that could happen: a success or a failure. So whatever happens, so we could turn a game into that. You either win or you lose. And again, that happens in a lot of different, like roulette. You bet on a number, you win or you lose. Dice games, sometimes you win or you lose. So what ends up happening is there's only two outcomes each time. And if you play the game several times, n times, a large number, what ends up happening, that this becomes a Bernoulli trial, right? We're doing the game, we're rolling the dice a million times. Every time we get a 3, we get some money. Okay. And so what we're able to do with this, since the probabilities are all the same, it's just so cool. But I remember just learning this as a formula, and I didn't really see it all together. I think I took out the part where it relates it back because it was just a little too much. But you just take how many times the probability of a success. And doesn't that make sense, that how many threes are, if X is 3, that means you won $3. And if you just take that probability times the number of successes, the number of n, that will give you the number of successes, which is in binomial, the number of successes, that is the random variable. Remember, binomial is measuring how many times we had success. Not necessarily how many dollars we won, but how many times we had a success, how many wins we had. Then we'd have to take that, if it was a gambling game, and multiply it by the dollars we won each time. But just the number of events times the probability of that event, because probability of success, probability of failure. And it's as simple as that. So if I had, what's the probability of what is the X? How many successes are there in 20 Bernoulli trials with a probability of 0.7? If P is 0.7, what is Q? 0.3, right? Q is that probability of a failure. So we either succeed at 0.7 or we fail at 0.3, but we don't need it in this one. We just take N times P, which in this case is going to be 20 times 0.7, which gives us 14, right? 0.7 times 10 is 7. So you could do that math fairly easy. And that makes sense that if you're going to win 70% of the time, you do it 20 times, you'll win 14 out of 20 times. That's 70%. That's all that's saying. Very simple formula. But I didn't look specific. I think there's 1 or 2 questions that have a Bernoulli trial in it. Sometimes they're hidden, though. They just say that but when you see them talking about a probability of success, think of Bernoulli. It's one of these things, binomial. Okay, so I remember reading one, and it doesn't specifically say it's binomial or Bernoulli, but it does say something about this many successes. Oh, that's the hidden word. Okay. Oh, there it is, 14. Here's another one. We're given the event f in some experiment. So see, it's not saying it's binomial. The event of some f in some experiment is 0.25. The experiment is repeated 100 times, and x is the number of times f occurs. So they don't say it's binomial, but that's, and they don't even say the word success, but that's what we're saying. X is the number of the times we get f. That's a sort of a definition of success. We have to see this is a Bernoulli trial. This is a binomial. It's just the number of trials times the probability of that success. That's all it is. Otherwise, we've got to do a probability distribution. But the other thing is, you can see they didn't give us a lot of information about what else is happening, right? So we can't really do a probability distribution. We can just say, okay, f is going to happen 0.2 times. We're going to do this 100 times. So we have 100 times 0.25. So we would expect 25 successes. So x would be 25. It's sort of the average, right? And again, it's not that we just do it 100 times and we're going to get exactly 25. But if we did this several times, we do it 100 and 100 and 100, and we do this trial many times, and we average those, we would expect we'll get closer and closer to 25. Okay, that's the theory. But you got to think of statistics. It's always, if you don't have something happening a lot, it's real. You're in a dangerous area of trying to apply statistics, because we've got all this variation. You get more variation, but you can try it, right? I think we're almost there. Here we go. And this is more like a homework question. Exam has 50 multiple choice questions, each having 4 choices. The student randomly guesses on each question how many correct answers can he or she expect to get. So expected value. But is this a Bernoulli? Is it a binomial? There's 4 questions, right? But what's the result? It's not so much about which one you chose. It's what? It's wrong or it's right. We either chose the right one or we chose the wrong one. So it's a Bernoulli. It's a binomial. And so the probability of getting it right, since there's 4 choices and we're just randomly selecting, is 1 out of 4, right? Although that's not really true, because we bring some knowledge in and we might be able to get, narrow it down to 2 or something. But let's just say we have no idea what we're doing, which usually is why we're guessing, right? I didn't study at all, so let me just randomly choose numbers. And so I got a 1/4 chance of getting it right, and I'm going to do that 50 times. So 0.25 times 50 is going to be, I think, like 12.5. You do the math, which I guess is what we're supposed to do. And we see, yeah, you get about 12.5 of them correct just by randomly guessing. Problem is a lot of times they'll get less than that because you lean one way or the other. You're not really guessing. And even if you really are, sometimes you can do better. But again, that's how it could work. And that's why, if we had 5, then you've only got a 20% chance. So that's why they give more and more choices on a multiple choice, so that guessing is kind of thrown out. It's not always possible. So if we take X to be the income of randomly selected lawyers, we're almost, actually, we should probably be done by now. That one's not right. I don't know that we're going to get this, but the other thing we can do is, the data is not quite there. The data was supposed to be here. So this is data of salaries for lawyers. 20 of them had between 20 and 29 and so forth. What we can do is we can take the midpoint of the data, here, here, and here. We take the relative frequency. So there was 200, I think 200, or however many lawyers there were. We take the average. So we divide 30 by however many there are. We get the probabilities, and we can we just take the probability times each random variable, where the random variable is sort of the middle point. Even though it's a large pile of data, it'd probably be too much to do. We can get a good estimate that on average, a new lawyer is making $54,000 a year. Okay, so there's something like this where you're going to need, they'll give you data like this table. You're going to need to get a frequency table, relative frequency, and that relative frequency becomes the probability of that happening. We multiply them, add them together, and get our expected value. Okay, and again, we'll have Friday as a work day. We've got our office hours. So, just kind of work through it. And then what we're going to look at on Wednesday is the variation in this, how spread out data is. So we've got our central data, central tendency. It's all this stuff, expected values. Wednesday, we pick up the variation in that data. And then we're ready to do our final parts with statistics. And again, it's just really an introduction to it. When you take a full statistics class, though, you'll be about 2 weeks into the course with all of what we're giving you. Okay, so you see, yeah, it's not too bad. And that's it. All right. Thanks for hanging out.